Hi, and welcome to my presentation about on-second order scoring rules for epistemic uncertainty quantification, which is a joint work with Eike Hüllemeyer and Willem Bagerman. So in our paper, we are interested in predictive uncertainty in machine learning and have a special focus on the different types of uncertainty awareness of a learner. To illustrate the usually considered three types of uncertainty awareness, let us consider a simple classification task with three labels. The first type of uncertainty awareness is when the learner's prediction is one of the here three labels. Since essentially no information other than the concrete label is given here when predictions are made, no uncertainty is reported, and we call this uncertainty awareness of zeroth order. The next order of uncertainty awareness is by making predictions in the form of a probability distribution over the labels. So the idea is to take uncertainty regarding the random outcome of the label into account. In the free class or free label example we see here, the prediction corresponds to a point in the 2-simplex, which is then consequently a distribution over the free labels. For the next order, one increases in some sense the expressiveness of the predictions, which means that now the learner can even predict the distribution over all possible label distributions. In this way, uncertainty about the underlying conditional label distribution can be taken into account. And it is worth noting that these three types of uncertainty awareness in the predictions are not only considered in classification tasks, but also in regression tasks. Now the question is how to train a suitable learner for these three different orders. So the first two orders are somewhat classical by now and can correspondingly addressed in a classical empirical risk minimization manner. All one it needs is a suitable loss function for this purpose. And a recent body of work proposes to train a second order learner in a similar manner, and for this purpose some loss functions are proposed. Now let us revisit how first order learners are trained based on the paradigm of empirical loss minimization. Here the concept of a so-called proper scoring rule is in the focus, and in particular the expected loss of a first order prediction p hat when the target prediction is p. The principle of proper or strictly proper scoring rules comes into play in order to distinguish then good loss functions from bad ones, so to speak. This is because they require formally that in expectation the loss is minimized when the first order prediction p hat coincides with a target distribution p. This property is of course desirable and gives the learner the incentive to be faithful regarding its first order uncertainty. And this is theoretically sound and is already quite heavily discussed intensively in the statistical literature and also in the machine learning literature. We can also give concrete examples of such loss functions, such as the widely used cross entropy, the Breyer score in classification, or the logarithmic score or quadratic score for regression tests. Now the theory behind loss function for first order predictions is well studied and appropriately established. What we now have asked in our paper is whether we can come out with something similar for the higher second order case. To this end, we have transferred the concept of first order scoring rules to the second order. Here it must be taken into account that the predictions are now on another level, so to speak, but the core statement for a proper scoring rule is analogous. Yeah? So a second order prediction is strictly proper if the second order prediction q hat coincides with the target second order distribution q. So accordingly, the second order loss minimizing learner would have just as much incentive to be faithful as in the first order case. The burning question is then whether we can find examples of such second order loss functions giving rise to a strictly proper scoring rules. However, we show in our paper that a huge class of second order loss functions are not proper, and in particular those proposed in the literature are included. So in the spirit of proper scoring rules, the learners using these loss functions do not faithfully report their second order uncertainty. For more detailed statements, take a look at our paper or visit me at my poster in Hawaii. Thanks.